We will get started in just 1 minute. I invite you all during the webinar, if you have any questions, to write your question at the Q&A box at the bottom. And at the end of the webinar, we will answer those questions. In addition, this webinar is recorded, and in 1 or 2 days after we edit the webinar, we will send you a link with the recording, which you will be able to share and watch the webinar again. And if you have any additional questions, you're welcome to contact me directly. So, Professor Pasquale Franciosa, the floor is yours.
Okay, so I hope you can hear me well. So thanks, Ami. So thanks, first of all, for inviting me to attend this webinar today. So let me start sharing the screen. Right. Okay. Can you confirm you can see my screen, Ami?
Yes, we can see the screen and hear you and see you well.
Okay, perfect. So let me get rid of this. Okay. Yeah, okay, so I think I'm ready to start. So thanks again, Ami, for the introduction, and welcome everybody. So I guess you are spread across Europe, maybe America, and maybe from Asia as well. So welcome everybody. So I was basically tasked by Ami a few weeks ago to say, okay, what about if we have a presentation talking on dynamic beam shaping with coherent combining for tailoring weld microstructure of challenging materials. So this was not an easy task, because obviously tailoring the weld microstructure using laser is like, you know, the holy grail. Everybody is trying to do that. So what I will do today, I will present our latest results using the CBC technology from Civan in trying to refine the weld microstructure in specific metals applications that are aluminum 6000 grade alloys. So the way how I've organized the presentation is basically in 2 parts. So part A will be a review of current technologies for shaping the beam intensity, shaping the intensity in time and in space. And then with that, we jump on the part B, which is more the testing data and experimental evidence from experiment we've been doing recently on some of the 6000 grade aluminum. The reason why we have been focusing on aluminum 6000 is because of the high crack solidification cracking sensitivity. And obviously refining the grain structure with those alloys is quite important, because if we do and if you succeed, there is a significant margin in improving the mechanical properties and the mechanical strength. So now let's start with the first part of the webinar. So as you can see, I've been focusing the attention only on multi-kilowatt CW near infrared lasers. So I've been omitting some of the other pretty well established technologies for beam shaping because they don't fit within the scope. So now what I will present you is mostly within this area. So don't be surprised if I am ignoring a couple of other technologies which are available there. So first of all, why we do beam shaping was the expectation and the benefits of implementing a beam shaping solution within our welding process. So we can probably divide across 3 areas. So first is about optimizing the weld profile, or controlling in a better way the weld profile. And this means eventually enlarging the process window, or bridging a bigger gaps between parts, which is very critical in many manufacturing environments. The second area, and this actually is also growing quite significantly, is the possibility of controlling the keyhole and in general the molten pool dynamics. So if we can do that, we can eventually reduce or control the porosity and the sputtering during the welding process, and eventually increasing the welding speed. So there is really significant research around area 2. there are people, I mean, all over the world focusing on different, approaches for controlling molten pool dynamics, including the molten pool shape. So the research is very established in this area. There are many contributions coming almost, I would say, every couple of days. And then the third, but not least important, is the possibility of controlling the microstructure, which is the main focus for today, actually. So controlling microstructure means eventually controlling the grain morphology, yeah, within the welds. With that, the possibility of controlling, reducing the crack sensitivity and phase formations and intermetallics. Intermetallics are extremely critical when you are welding mixed materials, which are prone to intermetallic formation. So now the question is, okay, great, we know the potential benefits of beam shaping, but what can we do to do beam shaping? And when we say beam shaping, it's not only the beam shaping in X and Y, or in Z, if you like. So beam shaping can be also done in the, like, on the focus steering, so X, Y, Z. But it's also about the time shaping, so shaping the intensity distribution also over time during the weld operation. Beam shaping is a very important topic, and you can see from the amount of papers which have been produced over the last few years. So, like, if you really see, probably 5 or 6 years ago, beam shaping, yeah, was growing, but was not very visible to the broader community. But then over the last, yeah, probably 5 or 6 years, yeah, starting from 2020, yeah, is almost exponentially growing. So the interest of people in research and people in applications and people in industry has been growing very, very significantly over the last few years. So this graph, I mean, we just took data from the Scopus database. We used, like, those keywords you see there with the beam shaping as an additional keyword, and you can see some of the statistics. So this proves, yeah, that beam shaping is an emerging trend within the laser material processing community. There are many contributions, and on our end, yeah, we're also investing time and resources to really understand more and more what we can do using beam shaping. Within e-mobility, so within the electrification and e-mobility sector in automotive, yeah, those are some of the core applications where beam shaping has been already deployed. Very common in those areas are application of wobbling and core ring technology, so central core and outer ring. Now, different materials, different thicknesses and different speeds involved brings different eventually properties of the beam shaping used. So now, why I say wobbling is a beam shaping? Because in essence, by using the wobbling with a galvo scanner, you are also steering the beam intensity on the workpiece. So that, to me, is classified as a beam shaping technology. But I will come back now in the next couple of slides, and I will show you how we compare wobbling technologies against the bigger picture of beam shaping technologies. So just keep it in mind. So in essence, there are two categories: static beam shaping and dynamic beam shaping. So with the static beam shaping, we can control the intensity distribution in X, Y, and Z, yeah, so in space. However, it's static, so it means that once we set it up, we can't change the distribution over time during welding. So it means there is no variation in time. Dynamic is adding the missing element. So dynamic means that we can control the intensity distribution in time and in space with different resolution of time and different resolution of space. So why dynamics is important? Dynamics is probably everything when we talk about laser material processing. So especially like laser welding processes, because the process is dynamic in nature. There are multi-microphysics involved. So starting from the porosity formation intermetallics, degradations, crack propagation, the plume propagation, keyhole collapse, sputtering, and so on and so on. So if you see the time scale, we are talking in seconds diffusions can be in seconds, can be even minutes, can be even hours sometime, but we go down to microseconds, so very small scale. So all those physics are happening eventually at within the time scale you see on the slide. So there is a clear dynamics, and the whole idea of using dynamic beam shaping is to influence those physics as they are happening in such a way we have a tailored response of the material properties in the end once the weld, the material is resolidified. So how does it work in practice? So when we say beam shaping, so starting from static solutions, so static basically means we are somehow altering the optical configurations within the welding head. So the simple solution is to add we call aperture elements. Typically, you can put just on the collimating path or on the focusing paths of the welding or the welding unit. So in essence, you are just limiting, the opening for your laser lights. Yeah, you can get some sort of shaping. This is not very efficient. It's not even too much used in industry today because you're literally wasting some of the laser energy and then not transmitting through. So more established is option C. So the possibility of using diffraction, DOE, and refractive optical elements, or also micro lens arrays, which again you can retrofit within the optical element. The benefit is the possibility of generating theoretically free shape distributions on the workpiece. Other options is also beam splitting. Yeah, so it's splitting the light in multiple spots on the workpiece. This is also quite established and works quite well if you want to really reduce the processing time, because you have eventually multiple beams running at the same time. So those are static options. So dynamics, you can see now. So within dynamics, we have a scanning based solutions. So very well known are galvo scanners, either single mirror or double mirror. So you can steer the laser beam in X and Y. The speed of scanning with the galvo scanner, we are in the range of kilohertz, so few kilohertz, thousand or few thousand kilohertz. The four bubble mirror is not very industrial deployed yet, but conceptually you have multiple mirrors which are electronically tilted in X and Y, and because of that you can get like a free shape profile on the workpiece. So the solution is quite interesting, but again it's not that fast. We're only talking few hertz modulation over time. Then another option is to use MPLC, so multi-plane line converter. So this also theoretically you can get a free shape profile on the workpiece, and we are talking in the few let's say tens of 100 hertz modulation in the end. So all those options E, F, and G are within the scanning family. So non-scanning families, so in-source solutions, yeah, we can probably group in two categories. So one is the fiber to fiber coupling, where you can get the very famous core ring configuration, so beam distribution. So this is very well established in industry. So this started probably 5-6 years ago. So there are a few different industrial implementations with this technology, but again, it's only limited to one shape, core ring. So if you want to be really free shape and we want to change within the millisecond, if not microsecond, the distribution during welding, then the solution is really what you see here using the CBC, so coherent beam combining with optical phased array, which is the Civan technology. So in essence, you have a matrix of, with the Civan, you have 6x6, so 32 single mode beams collimated, and then they are focused on the workpiece. So the way how it works, you are, well, not you, but the laser machine itself is modulating the phase between all those single mode beams. And because of the phase modulation, you can get theoretically and virtually any free shape on the workpiece. And on top of it, since it's fast enough, we are in the megahertz switching frequency. You can switch between shapes during welding. So there is a lot of opportunity and a lot of capability there. So yeah, so this probably I've already discussed briefly while I was explaining, but yeah, you can see the pros and cons of those technologies. And interesting enough, yeah, is on this level. So the possibility of controlling the temporal distribution of the beam intensity during welding. So with the static one, obviously there is no way of adjusting unless you are modulating the input power. With the dynamic options, yes, there is a possibility, but eventually you are limited by the switching rate. So using the CBC, you can go very high. So we are talking in several tens of megahertz, close to 80 megahertz. So there is a possibility of switching within few nanoseconds. So it's quite fast. And also more interesting is the scalability of the power. So with the CBC, with OPA, yeah, you can go very high power, so probably even more than 100 kilowatts today. So there is theoretically no limit on that. So again, there are benefits, but also obviously this brings more complexity. So now this is an important point I want to raise. So when we talk about dynamic beam shaping with the CBC, with OPA, we shouldn't assume that we can generate a static shape from there. So with the CBC, the shape is always dynamic. Yeah, it's always dynamic. So if you see now the example I put on the slide, and I say, okay, I want to create a shape with 3 dots, 1, 2 on the side, and then a central main dot in the middle. So we'll never see this profile on the workpiece. You will see always the combination over time, yeah, with a given dual time of the diffraction pattern. So the shape generated by the CBC is a combination of multiple diffraction patterns which are overlaid over time. So in essence, what we are controlling on the workpiece is the fluence. Yeah, so the energy we are throwing to the workpiece by overlaying over time multiple diffraction patterns. How many diffraction patterns? Okay, so it depends on the resolution of the beam intensity we want to get in the end. But theoretically, we can go to 1,000 diffraction pattern overlaid within as small as like 12 nanoseconds. So 12 nanoseconds is probably the limit with the lower limits today. But 12 nanoseconds, we can definitely control the solidification and the microstructure already. So it's already extremely fast. So this is probably another extreme. Yeah, so now we say, okay, I want to create a spiral profile, and probably the spiral you have seen from many of the other presentations from Civan and people working with the Civan technology. But again, spiral does not mean static on the workpiece. It means something like that. Yeah. So you can control the frequency of switching between those diffraction patterns. You can go very low in the frequency, so very high dual time, or other way around. You can switch with very high frequency, so very low dual time. So these are important points to remember, because again, by using this technology, we can really influence the thermal cycling, yeah, during welding by switching at high frequency, yeah, on and off those diffraction pattern. And one diffraction pattern, it basically means energy concentrated within those dots you see on the screen animated. Yeah, and this is a question now. So does it mean we can control the thermal cycling? And the answer is yes. So if you take a single Gaussian beam, so just the Gaussian dot in the middle, and you imagine you are moving the dot horizontally towards the right-hand side, that is exactly what you do when you do welding, because you are traveling with your laser beam on the workpiece, and you're plotting against the interaction time. So here you see interaction time at the same point. So here I'm tracking the position 0, 0. So the same point 0, 0 on the workpiece. I want to see how the intensity is changing as the point is, as the beam is moving horizontally in the direction. So with a single Gaussian beam, you will see basically the Gaussian profile on the workpiece. So very sharp transition of the intensity profile. So if you do the same exercise with the most fundamental pattern, diffraction pattern you can get from the CBC, you will see a central dot in the middle and then 4 satellites we call lobes, satellites on the side. Yeah, and you can see, you know, the cross section basically of the intensity profile with the lobe on the side. Interesting enough, if we add more than one pattern, so for example, we are overlaying 3 diffraction patterns. So, you know, they're very close with each other. So you basically, you can get like a slightly elliptical shape. Yeah, then you can see what's happening to the intensity profile. You're basically switching on and off, on and off. Yeah, and you can see how the intensity is going up and down, up and down. So by modulating the frequency or by choosing the right frequency for your process, yeah, it's like a duty cycle you can induce to your material. So duty cycle is what you do with any like pulsed laser, yeah, nanosecond, femtosecond, or you know, picosecond laser. You are controlling duty cycle. It's not something you do with the CW lasers. However, using the CBC technology, yeah, you are adding these additional parameters you can optimize, yeah, which is the shape frequency. And you can see 3 cases, yeah, which we have generated starting from the same sequence of clicks within the shapes. So those are probably 27 clicks. And then how the intensity distribution looks like when we are jumping from low frequency to relatively high. 20 kilohertz is not extremely high, but is relatively high already. And you can see actually how the pattern looks like. So now the question is, great, there is a possibility of modulating the intensity profile in as small as, you know, few nanoseconds. How that capability can help in influencing the grain structure. So can we use now this technology to really make changes to the grain structure? So conceptually is what you see on the slide. So we start eventually from the liquid phase. So the metal is in the liquid phase. Then because of the cycling, we are cooling down. And then again, after a few milliseconds, a few microseconds, we are pumping again some heat input within the weld. Yeah, and then you can see eventually the grain is refining. There is a, you know, the segregation is distributed, and then you get, you know, the property which is optimal for your application in the end. So that is the concept. Now let's put this concept in practice, and let's see how this looks like. So now this is starting the part B of this webinar. So, and I will focus on 2 applications around laser welding, autogenous laser welding of the 6000 grade aluminum. So why we have selected this application? First of all, 6000 grades are very well used within different industrial sectors, especially automotive, but also aerospace. So there is a significant, massive demand of those alloys to be welded. However, they're not very easy to weld, especially if you want to weld those alloys without adding any wire or, you know, altering the chemical composition. The reason why they are quite challenging is the high sensitivity to solidification cracking. And you can see from the video, from the high-speed video, the crack is, yeah, you can see there is forming just, you know, few milliseconds after the laser has gone through the material. And when there are cracks, yeah, it's automatically, you know, the weld is automatically not acceptable, so it's a scrap. So the cracking process is quite complex. So it's a complex interplay between, you know, different parameters and different physics involved. But in essence, yeah, it's a combination of microstructural and metallurgical elements together with, let's say, stress, strain related element. So there are some theories saying that the crack is happening because of the shape of the molten pool. So if the molten pool is very stretched and elongated, there is more crack sensitivity. If there is a chance of reducing the extent of especially of the machine zone, yeah, there is a chance of reducing the crack sensitivity. Other theories are also talking about the combination of a thermal gradient and solidification growth, so with the cooling rate. Other, again, research activities are saying, okay, the cracking is happening because there is not enough feeding of liquid between the dendrites, and that is causing micro pores. Yeah, and those micro pores are, you know, growing, nucleating and growing, and then in the end you get those micro cracks within the weld in the end. So cracking, yeah, as you can see, is a complex process. You know, people have been researching the reasoning for cracking and solutions to hot cracking for many years, but still is a hot topic in industry because we are still facing, I mean, challenges when welding those alloys. So to put in perspective, yeah, this is some, you can see here on the slide, some data of, you know, testing experiments we have been doing recently. So this was a comparison between different welding processes. So CMT on this end, then we have laser welding with addition of a filler wire. So it's a wire-fed welding process. And then autogenous welding, so only laser without even gas, no shielding gas even. And you can see the gap. Yeah, so there is almost, let's say, 30 to 40% drop in strength when you are welding those alloys fully autogenous. And 30% drop in strength from a certification point of view is automatically no go. So the end user, you know, will never accept that level of strength because it's not, let's say, satisfactory. Now, beam shaping. So we have been researching static beam shaping for some time. We have been doing different testing and different trials. You can see some of the, I mean, the schematics of some of the shapes we have been using. So starting from single core, then core ring with different diameter, and then even using like a tailed beam profile. So all those shapes are static, but you can see, I mean, the trends in mechanical performance, so tensile stress. Yeah, so there is, I would say, approximate 20% increase in strength when you go from a single spot to a tailed beam profile. So all those welds have been made with the same processing speed, so 25 millimeters a second on the same material and the same thickness. So this basically proves that even when we start with a static beam shaping, there is already margin of improving the weld performance. And why is that? You can see from the EBSD map that the reason why you have eventually increasing strength is most probably because there is a grain refinement, and grain refinement means you are increasing number of grain boundaries, and with more grain boundaries, yeah, there is a chance of increasing the strength in the end. That is only background information. So with that knowledge, we started working with the CBC technology, asking ourselves, okay, is there a margin of improving the properties even more? And is there a margin of tailoring the grain structure to meet the specific weld properties in the end? And this is where we started. So application one is an application on 61 aluminum. Is an overlap weld. They are quite thin, so 0.4 on the top and then 0.8 on the bottom, so 0.4 to 0.8. Yeah, and this is what we did. So so this basically is a comparison between the CBC technology from Civan. In this configuration, we are using the 1.5 meter focal length, which give the smallest spot diameter on the workpiece is close to, yeah, let's say 130 microns is the smallest one. Obviously, if you reduce the focal length, you will get the smallest spot. But in this project, we have used, I mean, 1.5 meters focal length. So welding speed was constant for all the experiments. So we use 110 millimeters per second across all the experiments. Power was, yeah, you can see the average 3.3, yeah, between 3.3 and 3.5 kilowatts for either single click or sequence of clicks. So clicks is understood diffraction pattern. So one click is associated with a single diffraction pattern. Yeah, no wobbling, no shielding gas, and the fumes were extracted, yeah, with a fume extractor positioned nearby the the weld area. So yeah, and then we have been benchmarking against the let's say more standard core ring technology. So again, you can see the speed was the same, the power was slightly reduced because the core spot was slightly smaller, and again the same clamping and the same welding conditions. So for the beam shapes, we started with, as you can see, with very, let's say, fundamental shapes. So only central lobe, so central spot with those 4 satellites, which are the consequence of the diffraction pattern with the CBC. And then we moved the point either to the left or to the right. Yeah, so by moving to the left-hand side is like adding a second spot into diffraction pattern. And this means eventually doing a preheating. Yeah, because there is a spot traveling in front of the weld and then preheating the material. If you do the other way around, so if you move the spot towards the right-hand side, it means it's a post-heating exercise because the side, the spot is coming behind. So this logic makes sense because eventually using the same laser, yeah, with the same input power, you have a possibility of just switching the spot forward or backward and then doing either preheating on the material or post-heating on the material itself. And we want to really see how now the weld microstructure looks like. So this is the full picture of the, with those shapes. So we went all the way from 0, 0, which is there, yeah. So from 0, 0, so all the way from a preheating to post-heating by moving the clicks within the diffraction pattern from left to right. So that is one set of experiment. The second set of experiment, yeah, is to have like a more like elliptical shape with the peak intensity either to the rear or to the front. You can see the animation of those clicks. So one click again corresponds to one diffraction pattern. And interesting enough, yeah, you can see there 6. Yeah, 6 there. It means that the diffraction pattern in that position is enabled 6 times more compared to the others. So in terms of time, it means that the diffraction pattern stays on the workpiece 6 times longer than whatever stays on the other points. And that's why in the end, if you combine all the diffraction pattern, you will see eventually shape that looks like what you see on the screen. So yeah, so with that logic, we generated those 6 profiles. Again, the welding speed was exactly the same, 110 millimeters a second. And the power, yeah, was adjusted to get the full penetration across all those welds. Yeah, and those are the parameters for the core rendering. Again, so the power has been adjusted in such a way we got to the full penetration on the weld. So the full penetration was the basic requirement to say, okay, the welds are comparable in terms of weld profile. Okay, so those are some of the images taken from the top. So it's interesting to see that when we start with the central spot, yeah, there is a nice fusion. Then as we keep moving the spot towards the right-hand side, so is adding more post heating. Yeah, still there is no significant crack, central line crack. However, when you go on the position 5, so it means the post heating is more aggressive. Yeah, there is a central crack happening, and then as we keep moving, yeah, then we have problem with yeah, blowout, probably a bit of humping, and even like lack of penetration on the bottom plate. You can see there is very extreme. There is a massive, let's say, blowout, lack of fusion, and yeah, lack of penetration on the bottom one. So this is the extreme case with the 2 dots front and rear. Now, if you do other way around, so if you do the preheating, so with the preheating, we are yeah, just opposite logic. So we switch towards the left-hand side, as you can see here. So the spot on the front becomes bigger and bigger as we are shifting, yeah, towards the left-hand side. Yeah, up to position 7, yeah, is almost central line crack free. Then as we keep moving more and more, behind on the left-hand side, then we can notice the presence of lack of fusion, some blowout there, and this again is a massive, blowout with a very significant lack of penetration. So now, if you analyze the cross sections, this was a very, clear evidence from all those experiments that when we are in the preheating, because of the preheating spot, we are preheating the material itself, and then the material, since it's very thin, we are only talking 0.4 millimeters. The tendency is to basically pre-bend before the main spot comes into it, and this is adding a significant, we call void there. So those void is basically caused by the preheating beam coming in front. That effect doesn't happen if you are on the post heating. So on the post heating is other way around. So we are only heating the weld what has been created, not before. So the warping effect is much reduced. So now, if we go to the analysis of the grain structure, so on the slide you see, some of the EBSD and EBSD maps, which are probably the most relevant one. You can see from the bar chart the distribution of the grain, equiax grain and columnar grain. So there is a trend, but more interesting is to see the full picture. So here, and this is plotting the area fraction of equiaxed grain. So starting from the only core beam static, beam distribution, to the tailed beam profile with a slightly, let's say, high peak intensity towards the front of this elliptical distribution. And you can see how the bar chart looks like. So you start from 25% area fraction of equiaxed grain, and then you ended up close to 55% of equiaxed grain. So this basically proves that by selecting, let's say, the appropriate beam profile, there is clear evidence that you can tailor your microstructure. So by tailoring the microstructure, and especially in this case, if you have 55% area fraction, it means there is 55% refinement. It means there are more grain boundaries, and with more grain boundaries within the weld, that the mechanical property of the weld eventually is going to be improved. So it's a stronger weld, because more grain boundaries means increase in mechanical performance. However, we have to pay attention to one element, that since with the diffraction pattern we have those side lobes created within the beam distribution, those lobes are not neglectable, so they account for approximate 35, let's say, to 40% of the total intensity distribution, and 35 to 40% distribution out of 3-4 kilowatts or even more is quite significant. And you can see the effects here. So this area and this area here on the left and then on the right is the direct consequence of those lobes. So when doing laser material processing like welding, but also additive manufacturing with this technology, we have to pay attention to the position of those lobes, because if we don't, we might have unwanted or unexpected defects, and we don't know why. So we have to keep an eye on those. So the second application again is on the 6000 grade aluminum, so 6082. So this time is thicker, 1.5 millimeter, and it's a bid on plate testing session we have done. So this time we have been like more creative. So we have been creating shapes which are more sophisticated. And again, you can see in the table like the power used. So we are between, let's say, 3 to 4 kilowatts, speed always constant, so 100 millimeter a second, and also the frequency was kept constant at 2 megahertz. And those are the set of shapes which are single. So this is a single shape. And then we also tested sequence of shapes. And again, from the table, you can see what is what. For example, shape, the sequence in sequence 22, we have a combination of the single spot. Yeah, it's there. And then after a few milliseconds, you can see there. So after 25 milliseconds, is switching to this vertical line, staying there for 5 milliseconds, and then back to the single spot for 25 milliseconds. And this goes on and on until the weld is completed. Yeah, and again, I mean, you can see now the details in the table. Yeah, so we've been producing, I mean, to make all those experiments, yeah, it takes time because we have to, you know, try the shape and then take, you know, all the metallographic section. So we produce all those experiments. And these are, again, some of the statistics from the EBSD maps. So now starting from, yeah, so 21. So 21 is the forward triangle, yeah, shape. Going to 15. So 15 is like one spot in front and then one vertical line straight behind. Yeah, we can see clearly grain refinement, and also quite visible is the refinement of the columnar grain. So comparing 1 and 15, so as expected, this is true for any welding process, we have more equiaxed grain towards the middle of the weld, and then you have a stretched columnar grain on the side because of the heat transfer dissipation towards, you know, the top and bottom of the weld. So, but comparing 1 and 15, yeah, the columnar grain are like quite high in aspect ratio. In 15, the aspect ratio is quite reduced. They are pretty much distributed along the y-axis. So the reason why there is change in the aspect ratio of those columnar grain is probably imputed to this effect. So the effect of, you know, modulating, pulsing, if pulsing is the right term to use in this case, but the possibility of modulating the heat intensity, the intensity distribution as you are, you know, passing through with the laser beam. And this is exactly what is happening. So again, by plotting interaction time for those two cases, so case 1 and case 15, I think the numbers are, yeah, it's the other way around, apologies. So this should be 1 and this should be 15, just, yeah. Right, yeah, so so by plotting the interaction time against the intensity distribution monitored at the same point within the weld, you can see how the intensity distribution is going up and down, and because of that thermal cycling, we see the response in the EBSD map in the end. We don't have thermal data yet because this is still work in progress. So we don't have evidence from the thermal distribution and from the cooling rate if there is any correlation, but there is clearly correlation between the beam profile distribution with a given frequency for creating and generating those shapes and the corresponding grain structure, yeah, produced in the end. So this one is showing some of the results with actual sequence of shapes. So this one you see, so is more than one shape. So for example, shape 30 is you are starting with a single dot in the middle, and then we have a sort of a ring going around, and then it's going on and off at the given frequency, and then same for other cases. And then again, we have evidence of grain change in the grain structure. So if you put all the results together, you can see the spectrum, how much, you know, the structure is changing. So focusing like at average size of the columnar grain, yeah, you can see you go from 150-ish microns up to 480 microns. If we analyze the aspect ratio of the columnar grain, yeah, there is probably, yeah, is a four times fold, yeah, change from 2 to 8, yeah, so aspect ratio of the columnar grain. Now, which one gives the best mechanical performance? Yeah, that is probably something we have to, do more testing, more characterization to say, right, now let's try to match this data to the tensile UTS data of the material itself, which is ongoing. So this is a live project we are currently focusing and working on. But the interesting result of this exercise is the possibility of tailoring the material properties of the weld in such a way you get whatever aspect ratio you want to see in the end for a given process requirement. So this is quite now interesting and fascinating. However, this open another question is to say, okay, great, we have all the flexibility and the possibility of tailoring the structure, but how do we choose the right shape for the right process and the right material? So the options are very endless. So the research now is really evolving, saying that we need the new tools and methodologies, to tackle the vast set of parameters which must be optimized to select the right shape. So with that, we are currently running one European project. So together with the partners from Europe and from UK, the project is called Laser for Mass. And one of the main target of this project is to deploy the dynamic beam shaping technology across multiple industrial sectors, and to tackle the complexity of selecting the shapes and make this technology deployable across multi industrial sectors. So you will see more and more in the coming months, because especially this Laser for Mass is a funded project with the multiple partners working on this topic. So stay tuned, because I'm sure you will see more and more coming in the coming weeks and coming months. So with that, I have done, and I think we are just on time to take questions and have a bit of discussion on some of the topics I have been presenting. So obviously, 1 hour I don't think is enough to cover all those elements, but at least I tried condensing the content within the time available. So I'm now more than happy to take any questions from the attendees. So Ami, I think it's for you now, because I don't think I have access to the questions.
So first of all, thank you for the fascinating talk. And I invite the audience to write their questions at the Q&A box at the bottom, and I will ask them. So first of all, you talked about it a bit at the end of your presentation, but the beam shapes you showed specifically in the shape sequencing that you have used, was there any reasoning or logic behind the sequences you used, or it was just random to see the differences between the different options?
No. The sequence, no. Obviously, there is always some sort of reasoning, either based on our experience or our knowledge with the response of the material itself. So the overall reasoning in selecting the sequencing is always to say, let's try to add a bit of a post heating to the material, to the weld itself, because if we do that, we know from theory that eventually we can influence the structure somehow. So that was the main reasoning behind. Then how we translated that reasoning in the actual shape, we said, okay, now let's see different shapes with different gradients, different extents in X and Y, and see how they look, how they look like.
Okay, thank you. There's a question, I guess this is referring to the beginning of your talk. If you can maybe just a quick answer, what is the vapor propagation?
Yeah. So that is understood. It's more the plume. So the plume coming from the keyhole from the molten pool. So it's the speed of travel of the plume of the vapor from the capillary itself. So that can be in the several hundreds millimeters per second. So there is a clear time characteristics with that. Let's say with all the physics involved within that process.
Okay. So as you mentioned, there is work in progress now on the effect of the mechanical properties due to the grain structure. What is your expectations at the moment to see the how would you assume that the grain structure would influence the mechanical properties from what you know now?
Yeah, so the assumption is about the grain boundaries. So if you look at the aspect ratio, or yeah, let's say especially the aspect ratio, or even the area fraction of equiaxed grain. So increasing the area fraction, it means we are increasing number of grain boundaries. So more grain boundaries eventually means more increase in the mechanical performance. So I'm not expecting one-to-one correlation because there are other elements behind. It's not only about grain structure, it's about also micro segregations and solute distributions, but the tendency is to say, yes, more refinement means increased in the strength performance, the UTS in the end. But we'll see. This is an ongoing activity, and we are aiming to publish this work also in the next couple of months. So yeah.
Thank you. Another question. Would you consider a second pass, which would treat as a heat treatment to also influence?
Okay, that's a very good question. So I would say theoretically yes. However, if you do multi-pass, then we are losing all the benefit of working with the laser technology, right? Because working with the laser, we want to be fast and reduce number of passes. So adding second pass, yes, but it's not very like what we want to do in the end. So eventually we want to do a single pass, and during single pass, we do the pre and post heating, if you like. Yeah, so you get the right property with a single pass. So nothing wrong with multi-pass, but I mean, conceptually is not what we want to achieve with the laser process, and even less with the CBC technology, because I mean, that is one of the reasons why we are adding this level of complexity to really reduce number of passes.
Yes, I guess it all depends on the application in the end of the day.
It depends, yes, but again, ideally, yeah, we go with as minimum number of passes as possible, ideally only one.
Yeah. Okay, this is, I guess, a bit of a different topic, but maybe you have a say on it. So how beam shaping can be helpful to achieve higher laser welding speed?
Yeah. Okay, so that is probably more for applications where you are in high speed, like 300, 400, 500 or plus millimeter per second, or even 1,000, in the 1,000 millimeter per second. And in those areas, we have issues like humping. Yeah, so because the material is solidifying too fast on the rear side of the molten pool, so whatever new melt comes out is basically ejected from the molten pool. So we have humping effect. So, and we also have another project where we are focusing on the humping for high-speed welding of high-strength steel. So the reasoning there is to, again, use some sort of shaping of the intensity distribution in such a way you can delay the solidification on the rear side of the molten pool, and if you can do that, yeah, the humping will eventually reduce. That is one area, so humping. Another area is to basically just increase the weld speed, and increasing the weld speed also theoretically means adding more instability, so more turbulence to the molten pool, and also more collapse of the keyhole. And is another, area for beam shaping, because reducing the number of collapse is, let's say, dependent by the dynamics of the molten pool itself, like the Marangoni force towards the top of the molten pool, then the recoil pressure within the keyhole, and the complex equilibrium within the keyhole wall. So we did some trials in the past by leveraging a central core with an outer ring, and the question was which diameter of the outer ring we have to use to have more stability or reduction in the keyhole collapse. Yeah, that was the main point. So obviously using a flexible tool like the one with the CBC, where you can either have a very small ring or very large ring, yeah, is probably the right approach. Plus the possibility of switching, the thermal cycling. That is an important element which sometimes is probably underestimated in terms of importance. But thermal cycling and intensity cycling, yeah, with in the megahertz regime is another parameter as a process engineer, we have to get used, because that is not like a standard, parameter we can use today on a standard CW laser.
So I will ask now the last question, and I apologize to those who I didn't reach their question. And this is a very interesting one, I find. It's talking about influencing the dynamics of the molten material. And the question is asking if you think you can push the melt pool backwards with using a shape sequence to try and compensate the drop of the static pressure in the melt pool.
Yeah, okay, that is definitely a good one. I would say, well, everything is possible in the end, right? So yeah, I think it's more about the application now driven, but there is also the possibility of steering, in the Z position. So rather than only keeping an X and Y, you can also steer in Z in up and down, again, with the same frequency, so in the megahertz regime, and that eventually can help in, steering the intensity in a different Z position. And by doing that, there is a chance of, pushing, the molten liquids, backward. So, because eventually you are changing the recoil pressure, so you have more or less recoil pressure, and this is altering the equilibrium on the wall of the capillary. And yeah, that might be a possibility there. It's a nice experiment. It's a nice experiment to try.
So definitely a lot more to experiment. So with that, I thank you all for participating. Thank you, Professor Pasquale Franciosa, for giving the fascinating talk. And wishing you everyone a good day, a good evening, depending on your location. Goodbye.
Yeah, thank you. Thanks.